In the last video, we started to look at the binomial expansion and in particular using Pascal's triangle to find the binomial coefficients. Let's take our binomial of a plus b to the power of n. We had now n was a positive integer and we could use Pascal's triangle to find the binomial coefficients. We had 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. So this gave us now up to the sixth row and we saw that it was symmetric. So if we wanted to expand to the power of 0, we had that line to the power 1, to the power of 2, to the power of 3, to the power of 4, and then to the power of 5. So let's just go ahead and expand this. What we'll have is a plus b, and we'll take this now to the fourth power. So we're going to have now the coefficient. The first one is going to be 1. Then we have a to the fourth, b to the 0. So what we have now is descending powers on the a term. We went from n to 0, and then on the b term we had ascending powers from 0 to n. Then we took our next binomial coefficient, which was the 4. We had now a to the power of 3, so we dropped the power, and then we increased the power on b now to 1. Both of these equal to n, 4 and 0, 3 and 1, plus 6, we have a squared, then we have b squared, plus 4, we have a to the power of 1, we have b to the power of 3, plus 1, we have a to the 0, and we have now b to the power of 4. So if we wanted to simplify this, we could say that that was a to the fourth plus 4a cubed b plus 6a squared b squared plus 4ab cubed plus b to the fourth. And those were the type of expansions we were looking at now in the last video. Now that's all well and good. We're only expanding now up to the fourth power. What happens though if we need to expand to the 10th power? Well, 11th power, let's take the 20th power. I don't want to constantly be writing out rows of Pascal's triangle. Instead, we have an alternative method. And this method, again, only holds true when n is a positive integer. And that method now is the nCr method. And we write it like so. When we read this out, we say it's n choose r. It's how many ways to choose r things from n items. Now that seems quite abstract. All we're looking at is the number of combinations. What we're going to do shortly is look at a practical example and see how this fits in to the binomial expansion. We're not going to go too far in depth with it, as essentially you can do these calculations straight through a calculator and you're not expected to have a massive grasp of what's going on at this level. So let's look at an example of nCr. So an example might be now 3C0. So if we wanted to read this, we could say now how many ways are there of choosing none of the items from a list of 3. Another way of writing that would be now 3 and then we'll put it in column form like so. So 3C0 and that's going to give us now 1. If we think about 3C1, this is asking me now how many different ways can I choose one item from 3 things. The answer is 3 ways. If we take now 3C2, this is asking me how many different ways can I choose 2 items from a list of 3. The answer is 3. If I now take 3C3, 3 choose 3, how many ways can I choose 3 items from a list of 3? The answer is 1. If we look now at Pascal's triangle, it corresponds to this row. So we can now use these as the binomial coefficients. So for example, if we wanted to expand the row where we have the power of 10, it would be 10C0, 10C1, 10C2, right the way up to 10C10. What I'm going to do is just look at how I found these and give you some practical example of what we've actually done here. What I'm going to do is take 3 animals. We're going to have now a cat, a dog, and let's have an elephant. That's nice and alphabetical. So what we have are 3 different animals. What we're going to do is look at choosing animals from this list. Now the first one I'm going to introduce is 3C0. This is asking me how many different ways can I choose none of those animals from the list where the list has 3 animals in. Well, the answer is quite clearly 1. I can only do that one way. If we now consider 3C1, this is asking me how many different ways can I choose one of the animals from a list of 3. Well, I could choose a cat, I could choose a dog, or I could choose an elephant, and that gives me 3 different ways. Let's now look at 3C2. This is asking me how many different ways can I choose 2 of those animals from a list of 3. So I could have cat dog, I could have cat elephant, or I could have dog elephant. There are 3 different ways. The order does not matter. All we're looking at now is the number of combinations. Let's now look at 3C3. This is asking me how many different ways can I choose 3 of these animals from a list of 3. Well, the answer quite clearly is one way. It's cat, dog, elephant. Again, the order doesn't matter. So what we're doing now is building up our binomial coefficients essentially by considering now these nCr values. So 3 choose 0 is 1, 3 choose 1 is 3, 3 choose 2 is going to give us 3, 3 choose 3 is going to give us 1. And we can just relate those back now to Pascal's triangle. So let's go ahead and see where that fits in with now the binomial expansion of a plus b to the power of n. So what I'm going to do then is have the following. I'm going to have a plus b, and we'll just start with a small power. Let's take this to the power 3. Now I could write this as a plus b, and then we'd have a plus b, and then we'd have now a plus b. When we looked at expanding this, we saw that the terms that we're going to get, so ignoring the coefficients, we'll have a cubed plus a squared b plus ab squared plus b cubed. So we can see the descending powers of a and the ascending powers of b. So we've gone from 3 to 2 to 1 to 0, and from 0 to 1 to 2 to 3. Okay, what we're going to do now is look at the terms that we're going to get. And we know that we're going to get 4 terms. If n is going to be equal to 3, we get n plus 1 terms. And those terms are a cubed, a squared b, ab squared, and b cubed. So let's go ahead and do it. So what we're going to have then is our a cubed, then we'll have a squared b, then we'll have now ab squared, and then we'll have b cubed. So the first question is, how many different ways can I make a cubed from that bracket? Well, the only way is to take an a from the first, an a from the second, and an a from the third. There's no other way. So we have a. And we could write this now as 3C0. This is essentially saying how many different ways can we write no b's at all. So the 0 corresponds to the number of b's in there. And we'll see later on when we get to 3C3, that will correspond to how many b's are in the list. Now let's look at the different ways that we can make a squared b. So if I took now a from the first bracket, a from the second bracket, and b from the third bracket, that's going to do it. A from the first, b from the second, a from the third, b from the first, a from the second, a from the third. We can see now that this will give us 3C1. It's asking me now how many different ways can I choose 1b from now these 3 brackets. So we can see that's 1, we can see that is going to be 3. What about ab squared? Well, let's start with bba. We need 2 b's and an a. We can have now on the next one bab, and then finally we can have ABB. So 3C2, that's going to give me now 3. So essentially this is saying how many ways can I choose 1B. This is saying how many ways can I choose 2 B's, which is these two things are the same, because what we're looking at here is the number of B's, and in here essentially we're looking at the number of not A's, and vice versa here. So this one right here is going to be B, B, B. B from the first bracket, B from the second bracket, B from the third bracket. That is 3C3, and we can see there's only one way of doing it. So what we end up with now are our binomial coefficients done by the method now of nCr. So when we think about nCr, all we're reading out is n choose r. It's the number of combinations, or how many ways to choose r things from n items. So hopefully that gives you some understanding. Now, going even deeper into this, we could look at how the formula is derived. But at the end of the day, our formula for nCr, let's write it here, nCr is given to be n factorial over now r factorial, and then we've got n minus r factorial. So in a later video, we might look at how exactly this works. But essentially, we can go ahead now and find binomial coefficients manually doing this. Now, when you have a calculator to hand, you might think, well, that's a bit unnecessary, but you might get a question that asks you now to write down a value. So what we're going to look at then, let's go ahead and look at 3C1. Now, if we consider what we've got n factorial. n factorial, if we have 3 factorial is just 3 times 2 times 1. So what we have when we have n factorial, we have now n multiplied by n minus 1 and so on and so forth. So we end up now in the numerator with 3 factorial. So what we've got then is 3 times 2 times 1 divided by now r factorial. Well, in this case we've got 1 factorial, which is just 1, multiplied now by n minus r factorial, which is going to be 2 factorial, which will be 2 times 1. We can see these are going to cancel, therefore we end up with 3. If we just think about 2 factorial is just going to be 2 times 1. So that's what we have. So let's now apply this. Let's say we wanted to find manually, let's say we wanted to find 5c3. So what we'd have then is 5 factorial over 3 factorial and then 5 minus 3 factorial, which will give us 2 factorial. So we can see that this is also going to be equal to 5c2, and that gives us a symmetry because essentially all we're doing is swapping these over. We can cancel a lot of this stuff off. So what we end up with then is the following, and we have 5 times 4 times, and I'm going to write this and be slightly cheeky with it, write it as 3 factorial. If we consider it, 5 factorial is 5 times 4 times 3 times 2 times 1, and we've already got 3 factorial here. So we've got 3 factorial, and then we're going to multiply that by 2 factorial, which is just 2 times 1. So they're going to cancel. In an exam, if you're asked to write it out, you just go ahead and simply write out 3 times 2 times 1. So from here, we've got 20 over 2, which is going to give us 10. If we go back to our Pascal's triangle, let's have a look where we were. Pascal's triangle now, what we've done is chosen either 5c3 or 5c2, and that's those two values there, and we can see it's 10, and we've done that manually. So we've done it manually, and again, you could, if you were asked to find, let's say we wanted now 10c8. So if we were expanding something now to the power of 10, what we'd have then is 10 factorial, and then we'd have over 8 factorial multiplied by 2 factorial. So if we consider what's going to happen, we're going to have 10 times by 9 times by 8 factorial, and then we're going to have now 8 factorial, and then 2 times 1. So what we're going to end up with now is simply these 8 factorials cancelling off. So we end up with 90 over 2, which is going to give us 45. So that now is finding 10c8 if we wanted to do that. So essentially what this is going to do, if we're expanding, let's have a look at an example of this. Let's say we've got a plus b to the power now of 10. So what we'd have now is 10c0. And then we'd have now, and we'd have a to the power of 10, and then we'd have now b to the power of 0. So now we would simply get down to what we're looking for, the term now 10c8. And quite clearly we can see that that could also be 10c2. So that value right here, if we were asked to now expand this, we could see that 10c2 would also be equal to 45. 10c0 is just 1, 10c1 is 10, and so on and so forth. So looking at this, it seems a bit complicated, but that's where the calculator comes in handy. So let's now look at this value right here, 10c8. We press 10, we hit shift, and we find the nCr button. And it's just there, it's the divide button. When you first start doing this, I absolutely guarantee you at some point you'll turn the calculator off. It seems to be a must. So 10c8, we end up with 45. In the same way, if we had 10c2, we can end up with 45. Because it's exactly the same thing as you can see. So let's go back to 5, choose 3, 5c3. And that gives us now our 10 in the same way that 5c2 would. So this is another way of working out the binomial coefficients when we're expanding. Now we can write this formally, and I'll write it out. If we have now, let's write this out, a plus b to the power of n, what we can write now is this will be equal to nc0. We will have a to the power of n, b to the power of 0. Then we're going to have plus nc1. We will have a to the power of n minus 1, and then we'll have now b to the power of 1. Plus dot 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 right the way up to ncn. We will have a to the power of 0, and then we'll have b to the power of n. And this now is the binomial expansion that you'll be given in a formula book. I personally think it's quite well, it's quite unnecessarily, it just looks a mess. But essentially all we're doing is now looking at finding these coefficients. So let's have a go at an example that we certainly wouldn't be able to do now using Pascal's triangle. So what we're going to do then, we'll go for 2. So let's make this a bit nasty. Let's go for 2, and then in fact we'll take 2 plus x. We'll raise this now to the power of 10. And what I'm going to do is find the first 4 terms in this expansion. So I'm not going to go through and do now 11, because we know that we get n plus 1 terms. We're just going to do the first 4. So what we're going to have then is 10c0. We're going to have now 2 to the power of 10, and then we're going to have x to the power of 0, plus 10c1. Now, when you're working out 10c1, you might want to go ahead and just think, well, that's going to be 10. A nice way of looking at that, that's going to be 10 factorial over 9 factorial, and then multiplied by 1 factorial. So quite clearly we can see that this is going to be 10 times 9 factorial, and they'll cancel off. So this is going to give us now 2 to the power of 9. Then we'll have x to the power of 1, plus 10c2. So at this stage you might be thinking, well, instead of trying to work it out, I'll use a calculator. But if you think about 10c2, we have now 10 factorial over 2 factorial, and then we're going to have now 8 factorial. So we end up now with 10 times by 9 times by 8 factorial over now the 2 factorial, and then we've got the 8 factorial. And we saw earlier that we could work this out because the 8 factorials are just going to cancel. 2 factorial is 2 times 1, so we have 45. So we could work that out manually, or we'd just put it through a calculator. So we're going to have now 2 to the power of 8, and we're going to have x to the power of 2, plus 10c3. So we're going to have now 2 to the power of 7, and then we're going to have now x, and that's going to be to the power of 3. So these are going to be now the first 4 terms. And we put plus dot 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 and so on and so forth, because quite clearly we've got 11 terms. We need to take that to 10c10, and we need to take the power of 2 to 0 and the power of x now to 10. So let's go ahead and write this out. So what we can have then is 10c0, and I'm just going to write this now as 1. Then we're going to have 2 to the power of 10, which is 1024. Then we're going to have plus. We know that 10c1 is just going to be 10. So that's going to give me 10. Then we're going to have 2 to the power of 9. 2 to the power of 9 is going to give me 512. Then we're going to have x to the power of 1, which is just x. Then we're going to have now 10c2. So we can use a 45, or at this stage you can simply plug it in. 10 shift, then the divide button, not the off button. You will do it. It's guaranteed. Then what we've got 10c2, so we've now got our 45, so we can see that from there. So we can put in now 45. In an exam you'd be expected to show this. Now 2 to the 8 is 256, and then we're going to have now x squared. 10c3, so if we wanted to work it out mechanically as it were, we can have 10 factorial, and then we're going to have now 7 factorial multiplied by 3 factorial. So if you like, what we're going to have is 10 times by 9 times by 8 times by 7 factorial over 7 factorial multiplied by 3 factorial, which is just 3 times 2 times 1. So from here we've got now 720 over 6, which is going to be 120. We can see the 7 factorials are going to cancel. That's a bit of a quick calculation, hoping I'm getting that right. Let's put this in. So all we need to do, if we weren't sure, is just flick it over, and we'd end up with 120. So then what we get then is plus the 120, and then we get 2 to the power of 7, which is 128, and then we're going to get now x cubed. And we'd go ahead and simplify each term, and we say that this is in ascending powers of x. So we've got x to the 0, x to the first, x squared. And again, you can just put these through a calculator and work them out, and just tidy it up, and you would be expected to do that. So that's a nice example of how we can use the nCr method to find the coefficients. In terms of working out where this idea comes from, I think we'll spend some more time later on that. But as you can see, this is quite formulaic, and often in terms of a particular unit you won't be expected to do anything other than work these out on a calculator. So that gives us some idea. But to have some understanding of the symmetry can really be helpful. So what we're going to do is start applying this now in future videos. If it's easier to use Pascal's triangle, I'm going to use Pascal's triangle. So for example, if we're expanding to a power 4, 1, 4, 6, 4, 1 is nice and straightforward. 1, 5, 10, 10, 5, 1. After that, we may as well go ahead now and use this nCr notation to find the coefficients. The actual terms are not going to be altering. So in this a plus b all cubed, we're going to have a cubed, a squared, b squared, b cubed. And then if we have now to the fourth power, it'd be a to the fourth, then we'd have a cubed b. Then we'd have a squared, b squared, then we'd have ab cubed, and then we'd have b to the fourth. They're not changing. This method is simply to find the coefficients, the binomial coefficients, when we have a positive integer value of n.